Hi, everybody. Welcome to the final lecture. Tomorrow's not really a lecture, it's a review, so we'll just call it what it is. We're going to finish up Chapter 10 today, and then we will be done with all of the content of Chem 121. Hooray! But we have to actually get there, so we'll celebrate later. Agenda items. Let's see. Last call for quiz number 8 is tonight. Make sure you get that in before the deadline. I accidentally clicked off my OBS. I need to make it bigger so I can read this. There we go. Quiz number 9 is due today, but it will close tomorrow. And then exam number 2 is on Friday. Remember, I sent an announcement out about this, that for exams and the final, you do this next week too. I'll send another announcement then. Your day to take the exam is 24 hours and is listed in the syllabus. For exam number 2, that is Friday the 11th. If you need me to move your exam forward or backward one day, I can do that. Send me an email and let me know which direction you want me to push your exam. And then I will hit a button and do that. I can't go further than one day because I don't release scores until I have all of the exams taken. And I don't want to advantage or disadvantage somebody by giving them extra information for whatever reason. So please make sure that you let me know if you want to move your exam date by the end of Wednesday. So by the end of tomorrow. Because once Thursday rolls around, you have to take it on the day that you have either already set it up on or Friday if you didn't choose a date at all. If you move it past that point, then I deduct points from your exam because you didn't do it in the time frame I gave you. So to avoid that, make sure you just tell me before the end of tomorrow. Okay. We're going to talk about the lab number 5 tomorrow. Lab number 5 is a worksheet that, again, I forgot what it is. It's one of two things. What do I have? Because I've changed it every so often. Let's see here. So, what is lab number 5? It's either solubility or pH. It is solubility. Okay. Okay. Yeah. So, lab number 5 is going to deal with solubility and stuff like that. We'll talk a little bit more about it tomorrow, very briefly, before the review, so that there's at least something there if there isn't anybody to ask questions for the review. Okay, let's go ahead and talk more about pH. So we left off yesterday by me leaving this picture on the screen. And we defined acids as things that had a pH lower than 7. In addition to all the aforementioned properties we talked about acids, like they taste sour, they dissolve metals, they neutralize bases, etc. And then we define bases as things that have pH above 7, so a larger number. And also along with the properties of bases being that they react with fatty acids and make things slippery. They're good cleaning agents. They taste bitter, etc. So, using everything that you've learned so far in this class about acids, bases, pH, etc., what I want you to do, and I'll number these for you, is... I can't find the cursor. There it is. I want you to tell me, for each of these things, 1 through 6, acidic, basic, or neutral. So I've given you some hints, and yeah, just type it in the chat. That's really all I have to say about that. This shouldn't take you more than 3 minutes, so I will start my little timer here, and I'll see you in a bit. All right, let's go over the answers here. So we got a solution with pH 3. 3 is lower than 7, so that's acidic. We got a solution of baking soda, pH 8.5. That's above 7, so that's basic. Orange juice is also acidic. It's got citric acid in it. A glass of deionized water, pH 7.000. That would be neutral. And then HCl, it dissociates into an H+. That's acidic. And then KOH, if you use the Arrhenius definition, it has an OH- in it, so it must be basic. If you use the Bronsted-Lowry definition, OH- would react with H+ in solution and lower the amount of H+. So either way you go, it's a base. All right, let me know if you have any questions. How do we calculate pH? You are going to need either a calculator or a calculator website online. Now, if you don't have a calculator, you can always just type a calculator into Windows. So what I'm going to do is I'm going to capture my calculator app here. And I got to make sure it has the right key on it. Oh, it totally does. Look at that. Okay, so let's add a window. Window capture, calculator. That's not a calculator. That's a calculator. All right. We're going to put the calculator right here because nobody's using the chat right now. If you do, I will move the calculator. All right. How do we calculate pH? We're going to use this button right here that says log. So the formula to calculate pH is minus log with a 10, specifically. I'll talk about what that means in just a bit. Concentration of H3O+. So let's analyze what all of this means. So this is the concentration of H3O+ in moles per liter. So whatever the molarity of your solution is, you're going to enter that in to the log expression. Is there a bit of leeway with things that are neutral? I have to actually move my calculator because I can't see the chat again. Yeah, if you're like 7.1, you could call it neutral. I'm not going to do that to you. So, just FYI. Now, what the heck is log? What does log do? What log does is it is the opposite of this function. So if I plug in a number for x, I will get y out. So for example, let's say if x equals 2, then I would get 10 to the 2 equals y, which equals 100, right? Because 10 squared is 100. Log is the opposite of this. So if I do this, log 10 of this, and then I log 10 this side, what will end up happening is that the log 10 and the 10 to the will cancel each other out, and I just get x. And so what that means is that if I take log of 100, I should get 2, right? And so we can see that in the calculator. So if I hit log on the calculator here, I didn't actually enter a number. So you may actually have to do that. So I'm going to type in 100 and I'm going to hit log and it'll just say 2 because that's the answer. So that's how log works. Sorry, clearing my throat there. Log is the opposite of 10 to the x. And so you can see that those buttons are right here next to each other. Now, there's this other button down here that says ln. This is natural log. This is not a button that you want to use for pH, okay? So don't use the ln button on your calculator. Use the log button instead. Now, if you're typing something in Wolfram Alpha, which I'll get the website here in a second. Oh, I gotta capture it, so because you can't see it. Wolfram Alpha. There we go. All right. So if you're in Wolfram Alpha, right here, and I can actually paste this website for you. I use Wolfram Alpha as a calculator when I just don't want to type something into a calculator. Like if it's just too long, you could type it in here. So if I type in log 10 of parentheses 100 and hit enter, it will tell me 2. Let me make sure that's on the screen there. Now, the reason that you have to type in 10 is because you could have log of anything. If you just type in log of 100, you get this random number, seemingly. And what it's actually doing is thinking that you're trying to type in ln. ln should give us the same number. So that's why I put the 10 there. Oh, you can't actually see this pop-up, can you? Oh, you can. You totally can. Okay, cool. So, again, if I get rid of this 10... then the result that it's thinking is, oh, it's like you're trying to tell me to do ln, because you're trying to do natural log, which we're not. So if you're using an online solver, make sure that you have the 10 in there so that you get the correct answer. Otherwise, you'll get a totally bogus result, because it will Wolfram Alpha will think that you're using this button right here. Okay, so let's get rid of that. You know what I should do? Let me just do this for today. We'll just do that. There. Now if the chat goes off the screen, it will scroll. Oh my goodness, you guys, I could have had a calculator on the screen this whole time? Why didn't I think of this? Oh, it's such a good idea. Oh, I feel so silly. Also, you can kind of see what's behind when I'm scrolling, so now I'm in front of the chat. This is kind of fun. Whee! Okay. Sorry. Oh, that's such a good idea. I'm going to do that from now on. Next quarter, I'm just going to have a calculator on the screen. Okay. Now, when you're printing a pH number, there are rules for sig figs with logs, but we're going to ignore them because you guys hate sig figs already. So what I'm going to ask you to do is whenever you take the pH of something, always use 2 decimal places and then however many 1s and 10s that you get. So, like if I did like, I don't know, 0.285 log. So if I was writing the pH of this, I would also have to negate it. And so I would report these digits, 0.55. The 4 becomes a 5 because I'm rounding. Okay. Okay. So let's do an example here. I want you to type this in your calculator. I want you to type in minus log and then 1, and you should confirm that you get 0. And so I'm going to do that too. So I'm going to go log 1 and then negate it. So negative 0 is not a thing, so the negation of 0 is 0. And then I want you to try this one. I want you to put 4 molar HCl and confirm that you get negative 0.6. Remember, you have to negate it after you're done. So if you just take the log, you're going to get a negative number. You need to turn it into a positive number for most cases. In this case, you're going to take the log and you're going to get a positive number, and then you negate it to make it negative because it's so acidic. So we're really not going to be using 1 molar HCl or things like that with pH 0 very often. In fact, it's of more interest to us to look at the pH of things that are much more dilute. Okay, so hopefully you have played around with your calculator and can confirm that you can do that. So now that we've done that, I want you to tell me... oh, no, never mind. I don't have any more examples here. So I'm going to make up some more examples. Actually, no, what we're going to do... So we're going to go over here. And let me capture the calculator again. We'll put that over here. Now what's going to annoy me is if I go like this, it's going to move slightly, isn't it? Yeah, I could fix that later. That's close enough. Okay. So let's figure out how acidic something is that's pH 7. Now, we've been saying this all along, that if you have a pH lower than 7, you're acidic, and if it's higher than 7, you're basic. But what does that mean for the amount of acid that's actually in the solution? Well, we can solve for this, because remember that minus log of the amount of acid that's in your solution will equal the pH. Now, the first thing I'm going to do to solve for this is I'm going to move this minus sign over to the other side. And so that's going to make my expression this. And then I told you earlier that log undoes 10 to the x, right? So we said that if I had 10 to the x equals y, that if I log that, then the log and the 10 cancel out, and I get that, right? I can do the opposite to undo log. So if I do 10 to the power of this, then the 10 to the and the log cancel. And then I have to do the same thing over here. So now this becomes how much acid I have is equal to 10 to the minus pH. And since my pH is 7, the amount of H3O plus in my solution would be 10 to the minus 7 moles per liter. Or specifically, 1.0 times that. So the amount of acid in something that is pH neutral is very, very, very low. Water naturally has 1 times 10 to the minus 7 moles per liter of H3O plus in it. Now, in a more advanced class, like for engineers, in Chem 163, we will actually talk about how you get this number in a different way, by talking about the autoionization of water. What that means is that water, being a covalent compound, is very, very stable, and those bonds are very strong. But even so, a small amount of water molecules do dissociate, as if they were ionic. And the amount of H plus that you would get, because if water dissociates, it would turn into something like this, right? And so remember that this is H3O plus, and the amount of that in the solution where this naturally occurs is this number. So this is where pH 7 comes from, is we can measure that amount and then take the log of that and you get 7. So this is just an idea of the concentration of acid that you're going to be working with. It's super, super, super small. Why is the pH scale from 1 to 14 and not, say, 0.01 to 1? Because we just arbitrarily decided that we were going to use log as our rubric. And the reason that we decided that is because the amount of acid ranges from approximately 1 molar to this. And when you take log of these numbers, so log of this becomes 0, and log of this becomes 14. After you negate it, that is. So that's our range. It's because we are just working on this huge scale. So 10 to the minus 14 is very small, all the way up to 10 to the 1. So we need something to accommodate amounts of acid that can range 15 orders of magnitude. And so the log scale works really well for that. That's why we do it. That's a bit more into number theory and, like, why do we... Like, we just made this function that does this. All right, let's go back over here. All right. Now, when we are entering numbers in for the concentrations of an acid, you can only enter this number if the acid is a strong acid. Because remember what strong acids do. We're going to use HCl as our example here. That's not what I meant to write. I meant to write H2O. Remember that for a strong acid, we only have the forward arrow here, right? And so whatever amount of this I put in here is going to be this amount at the end. So if I had like 0.05 molar HCl, it would all dissociate, and I would then have 0.05 molar H3O+. So that's only true if we have a strong acid. If we have a weak acid, then we don't actually know how much H3O+ is in the solution without doing some math. We're not going to do that math in here because I spend 3 days teaching students to do it in 161. We don't have 3 days. We have about 30 minutes to talk about this, so we're not going to do those calculations. Instead, what I will say is that if you have a weak acid, then this number will just be given to you. And it will say, the problem that you're looking at will say something along the lines of, this weak acid has an H3O+ concentration of, and then a number. And then it'll ask you to calculate its pH. Now, this is all great and wonderful if you are working with an acid. But what do you do if you're working with a base? Because the equation wants the amount of H3O+ in the solution. But if you're given a base, you might only know this number. So what do? Instead of doing pH for bases, we can do the pOH, which is the exact same formula. It's just that you put in the concentration of OH in moles per liter into the equation, and what you get out is the pOH. And then you can turn pOH into pH by doing this. So whatever you get for pOH, do 14 minus that number, and you will get the pH. So for instance, if I did, I don't know, let's see here. So let's suppose that I had OH equals 0.00250. So then what I would do is I would say the pOH would be I wrote this stupidly. Hold on. So the pOH would be... the pen's not working now. Minus log of the OH minus concentration, which would be this. And so when I go to the calculator to do that, we would get 0.00250. We'll log it, and then we'll negate it. And so I got 2.60 is what I got. And then we could say, well, this number goes in here, and then 14 minus 2.60 equals the pH. And so the pH would be 14. Oops, I got to actually click on the calculator. 14 minus 2.60. And then 2 decimal places because that's what we need. So there you go. So this is how we can get pHs that are higher than 7 out of this equation, because generally speaking, I'm not going to give you the H plus concentration for a base. I'm going to give you the OH minus concentration, because that's an easier number to conceptualize. All right. So I want you to try this example. I want you to tell me what the pH of 0.250 molar sodium hydroxide is. Do the calculation using the pOH formula, and then turn that into a pH using 14 minus pOH. I'll give you like 3 minutes to do that. Report your answer in the chat when you get it. One more minute and we'll go over the answers. All right, let's do the solution to this. So if I do minus log of the amount of OH minus we have, that will give me the POH, which would be, I've got to go back over here. So I got 0.250. We're going to log that, and then we're going to negate it. So we get 0.60. And then 14 minus POH equals the pH, which would be 14 minus 0.60, boop, 13.4. So you can see that low concentrations of base, strong base anyway, end up having very, 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 very high pH. So sodium hydroxide is extremely dangerous to like a biological system, which is why we use it for cleaning, because if we're trying to clean something, we want biological matter on our pots and pans, for example, like greases and grime and fat. We want that to just be gone, right? So we want to try and like dissociate it or obliterate it, more likely, as much as we can. And so base is very effective for that. All right. Now, remember that the POH only works for strong bases, just like pH only works for strong acids. All right. I'm going to give you 3 more problems here. So for problem number 1, I want you to tell me the pH. Oh, I'm going to sneeze. Okay, I muted in time. Sorry. I want you to tell me the pH of this weak acid, which has a very low concentration of acid in it. For number 2, I want you to tell me how much H3O plus is in blood. Remember that if pH equals minus log of this, that you can undo that and get the concentration to be that, which I had to cram in there, 10 to the minus pH. And then for number 3, tell me the pH and POH of HCl, if it's 14 molar when we sell it. I'm going to write down the formula again for this. There's that formula if you need it. Now, if you know pH, you still can solve for this one. You just have to move things around. And yes, you are going to get numbers that are outside the range of 0 to 14 there. So go and try those problems. I'll give you 5 minutes, and we'll go over the results in just a bit. One more minute, we'll go over the answer. All right. So I need to go over here. Oh, I gotta click there so that's not on my screen. All right, let's do this right here. And we've got pH equals minus log of H3O plus. And I know that the concentration of H3O plus in the solution is 5.35. Oh, 5.25, sorry. 5.25 times 10 to the minus 5. So let's type that in the calculator here. So let's see here. 5.25 times 10 to the minus 5. So there's 5.25 times 10 to the minus 5. Windows calculator prints like a lowercase e to represent that, which is not great, but we're going to log that. Boop. And then we're going to negate it. Boop. And so I got 4.28. There you go. Oh, that's why my cursor isn't showing up. I keep holding my pen in my hand while I'm trying to use the mouse to move, but if my pen is over here on the tablet, it moves the cursor back over to the other screen, and then I can never find the mouse. Like, why isn't it working? Because I don't know how to use my mouse. All right, for problem number 2, here's the pH of blood. You do not want the pH of blood to go much further outside of that range. 7.3 is what you want. If you even go like 0.5 out of range, very bad things happen to your body. So I need to figure out how much acid is in the bloodstream at this pH. And so that would be, well, if I take this equation, and I move the minus over so that this goes away, and then I do 10 to the power of all of that, 10 to the power of all that, this cancels out. And this equation would give me the amount of acid in the solution. So I would write 10 to the minus 7.30 is how much acid is in there. And then we'll type this in the calculator. So here we go. So clear everything. So 7.30 negate 10 to the x. Boop. There you go. And so I get 5.01 times 10 to the 8. And so I would write this. And again, that is all concentrations are in moles per liter. All right, and then the third problem. So again, pH is minus log of H3O plus. So if I want the pH of 14 molar HCl, 14 log negate. And then I just take the first 2 decimal points. So I get negative 1.15. And then, remember that 14 minus POH equals pH. And so that must mean that if I want to solve for POH instead, I could just swap these two, right? I'll add POH to both sides and subtract pH from the other side. And so my equation would then look like this. And so that would be the POH of the solution. For POH, think of how the pH scale works and just do the opposite. So if you have a very high POH, you have a very acidic solution, because a low pH would be an acidic solution. A very high pH would be basic, so a low POH would be basic in that case. All right. Now, really, the way that you get your head around this is to play with the numbers. Do as many of these problems as you can off of the worksheet, as well as the practice problems that are recommended in the text right here. Excuse me. Because that's the only way to really become familiar with these numbers. Otherwise, it just looks like I'm throwing random numbers at you. What the hell does negative pH mean? What the hell does, 15 POH mean? And the more you work with it, just like anything really, the more it'll make sense to you. But we've shown how to do the math here, and it's pretty straightforward. So let me know if you have any questions about that. All right. Why do we care about pH? These numbers I took for a presentation when I did a pH lecture in 2005 or 2006. So these numbers are not necessarily super accurate, but they're probably close. Now, if you go and measure the pH of the ocean in around the year 2000 was about 8. I believe it has since gone down to 7.7, 7.8, or something like that. It is decreasing. Rainwater is about 5.6. We're going to see why in a second. I told you that we were going to mention that today when we had a lecture yesterday. And if I measure the pH of water around Edmonds, I get this number, 7.4 to 7.6, was what I could find online. Now, if you have pHs that go out of these ranges, so pHs around 1 or 2, or 13 or 14, you get weird effects. And those effects are interesting to study, but may not necessarily be good for the environment. So here are some examples of that. The first thing that we notice is that rainwater, way more acidic than you'd expect, right? It's just water. It should be pH 7, but it's actually pH 5.5. Excuse me. I need to drink more water today. Now, the reason that rainwater is acidic is because there's abundant CO2 in the atmosphere. Abundant enough, right? I mean, we make a lot of car exhaust and other things that cause CO2 to be released into the atmosphere. When water combines with CO2, you get H2CO3. This is carbonic acid. Carbonic acid is a weak acid, and it will dissociate enough so that the pH of something that carbonic acid is in will be about 5.5 at ambient conditions. Now, what if you are in an area where there is worse things than carbon dioxide? For example, sulfur dioxide. Sulfur dioxide forms from industrial practice. So if you smelt metals and those metals contain sulfur in them, the sulfur needs to be removed somehow. And it typically ends up just being combusted to form SO2. SO2 will react with water to make sulfurous acid, and sulfurous acid will react with water further to make sulfuric acid, which is a strong acid, we're told. And the more of this sulfuric acid you make, the lower the pH can go, all the way down to 0 or lower. Now, pH 0 rainwater raining down on your head would be catastrophic. Like, it would burn. It would actually hurt you. Fortunately, there's not that much sulfuric acid out there. But there is enough in specific parts of the country to drastically alter the pH of rainwater around those locations. And you'll notice that these are all centered around one specific place. Right here. That's not where I meant to touch the screen. Not right there. Right here. What is right here? Where I'm drawing this red X that you can barely see. Anybody know? Let's do purple. Yeah. What does that red purple X represent on the map? What city is that? Give you a hint. They have a football team that gives away this whole discussion. No, that's Michigan. Flint is in Michigan. That's next door. That's a good guess, though, based on the context. So that state that I have drawn the X in is Pennsylvania. Oh no, this is not a geology or geography class, is it? It's not Boston. That's Massachusetts. Keep guessing. Philly is the other side of it. What's the other one in Pittsburgh? I just said the answer. What's the other one in Pennsylvania? It's not Philly. You guys need to either look at a map or actually go places. Although right now, I guess that's kind of not a thing we can do. But yeah, it's Pittsburgh. Yeah, and what football team is in Pittsburgh? Yeah, it's the Steelers, right? What industry is real big in Pittsburgh? Yeah, that's where all the steel manufacturing is, right? All of the steel manufacturing in the United States in like was established in this area, right? All around Pittsburgh. And look at what it has done to rainwater pH. It's such a fascinating thing. And you can actually see that from this map. Like, it's entirely centered around Pittsburgh. Now, over and towards the west, we have much higher pH relative to Pittsburgh because we don't have as many steel industries over here. Like, we don't have that much air pollution relative to the East Coast because they have a lot. It's all more established there. It's been there forever, right? I've been to Pittsburgh, and I actually really like Pittsburgh. And yeah, it's all defunct steel mills and some that are still operating. So these numbers were taken in 1996. They're 25 years old. Probably more than that, actually, now that I think about it. 26 years old, okay. What are the effects of low pH water? So if you have things that are susceptible to acidification, such as limestone or marble, so like public works, things that are made like from materials that are susceptible to acid, they tend to erode in places where acid rain falls. And so I have a picture here of a statue that has basically been dissolved away slowly over time by acid rain. If you have metals, metals tend to corrode in the presence of acid too. So corrosion is much more prevalent on the East Coast than it is on the West Coast. With regard to acid rain, there are other reasons corrosion can occur, such as salt. So if you live next to the ocean, you're kind of screwed either way. But Pittsburgh is nowhere near the ocean, and they have to deal with all these problems pretty much all of the time. All right. Hopefully that was informative. We're going to take our break now, so we'll go to the timer screen here. I'll start the clock, and I'll put the music back on, and we'll see you in about 10 minutes. There we go. We are back. All right, we have 2 sections left. One of them is about salts and pH, where we're going to just put random salts into water and see what happens to the pH. And then the last one is a buffer, which is a mechanism for resisting pH change. So let's get started here. Okay. When you mix a salt into water and it's soluble, the salt will dissociate. And depending on what the salt can do, it will react with water, which is amphoteric. Or, I'm sorry, amphiprotic is the word I wanted to say. That is going to cause the creation of either H3O plus or OH minus. Or neither, if neither of them reacts. For example, if I put sodium chloride in water, it will dissolve, but what will it do to water? If I look at these substances, sodium is not reactive towards water, right? So this would do nothing. And then this is the conjugate of a strong acid, which means that it's effectively neutral, right? If it's neutral, it's not going to do anything either. And so the effect on water is that water just remains water, and the solution will be neutral. So putting table salt in water does not change its pH. But what if I put in a salt like this instead? So we're going to put in sodium nitrite. Sodium, again, would do nothing in water. It's attained its octet. It doesn't react. It doesn't interact with water in any way. This is nitrite, which would be the conjugate of HNO2, which is a weak acid. Remember that this is not one of the 7 strong acids, HNO2. HNO3 is the conjugate of or HNO3 is a strong acid, but HNO2 is not. Because it is the conjugate of a weak acid, that means that this must be a weak base. And what do bases do when they interact with water? They would do this, right? So I would take an H and put it onto this because it's a weak base. And then I would create this in solution, so the solution would be basic. So what we're going to do is we're going to be looking at what ionic compound we drop into the solution. And we're going to look at the parts, and we're going to say, okay, what do each of those parts do when they come into contact with water? And to analyze that situation, we're going to consider what they are conjugates of. If we know what the conjugate does, we know what this does, because it does the opposite, right? If something's conjugate is a weak acid, then that means the conjugate of the weak acid would be a weak base. And so on and so forth. So we're going to look at 4 different situations that will affect the pH. So the first one's the neutral situation. If I have a strong acid and a strong base, the salt that I make is neutral. And when I put this in water, nothing will happen. So when I give you a salt, like for example, say, let me clear this out of the way to make more space here. Like if I gave you, say, this, or maybe that, the conjugates of these would be, for Cl would be HCl, which is strong, and then K probably came from KOH, which is also strong. The conjugates of strong things are neutral, so that means that this must be neutral. Same thing down here. So rubidium and iodide would come from HI and then RBOH. Those are both strong, so this would be neutral. So if you put table salt in your water, you're not changing its pH at all. It'll still be pH 7. All right. What about something like this? If I have a salt that looks like this, then what we can infer is that ammonium and chloride are my ions. What's the conjugate of ammonium? It's ammonia, which is a weak base. So therefore, this must be a weak acid. What's the conjugate of Cl minus? It's HCl, which is a strong acid. So its conjugate would be neutral. And so we don't care about it. So now the question is just, well, we're going to put this in our solution. What will happen when this reacts with water? Well, if I have a weak acid plus neutral, the solution will be acidic because the weak acid will react with water, pass over an H plus to make H3O plus, and the solution is acidic. All right. So if you see NH4 in your salt, NH4 is a weak acid because its conjugate is a weak base, so therefore it'll make the solutions acidic. What about something like this? This is the example that we just did. This conjugate is, or sodium plus is just worthless. It doesn't do anything to the solution. This is a weak base because its conjugate was a weak acid. So if we put this in solution, it will be slightly basic. The last circumstance that we can run into is what happens if we have both a weak acid and a weak base. So in this instance here, we have an issue. This will dissociate into NH4 plus and acetate. The conjugate of NH4 plus is NH3, a weak acid. So that means that this must be a weak base. The conjugate of acetate is a weak... Oh, shit. Hold on. I messed up over here. I wrote weak acid over here. I meant to write weak base. NH3 is a weak base, which means NH4 plus would be a weak acid. Acetic acid is a weak acid, and I was looking at this and like, wait a second, why did I write the same thing? Which means that I have a weak base in acetate. Now, if I mix a weak acid and a weak base together, how will they interact with water? And the answer is we don't know. It could go either way. There is a way to calculate it, but it involves a lot of math that you don't want to do. We're not doing that in this class. I make my engineers calculate it. You don't have to. So those are the 4 scenarios. You're going to be looking into your ionic compound. I'm going to say, what happens when you mix this with water? What will happen to the pH? And you're going to look at the ions that form, and you're going to look for weak acids, weak bases, both, or neither. So let's do this as an example. So the first step that we do is dissociate. What does this dissociate into? It dissociates into sodium plus, which does nothing, and chlorite, ClO2 minus. Let's look at the conjugate. Was this on the list of strong acids? Turns out it was not. That means that this must be a weak base. And a weak base plus water would make this. So adding NaClO2 to water would be basic. So again, you're going to be looking at the parts of the salt that you add to water. Look at the conjugates of those parts to give you an idea of what the parts themselves do. So ClO2 minus, you might not know what that is, but you know its conjugate is not in the list of strong acids that we talked about yesterday. All right, and then there's me doing the problem for you on the screen. I'll just put that back up here. All right. This is actually complex because it takes a lot of steps of thought. But I'm going to have you try this one. And I want you to split this into its parts. Let's write down what I want you to do here. So just in case you need it written out. So split the salt into ions. Then I want you to check the conjugates to see if they're strong or weak. And then tell what the salt does. So do those steps in that order. Remember that any neutral ions that you get that are metals, you can just cancel them out because they already have fulfilled the octet rule. We don't care about them. Go ahead and give me the answer either acidic or basic in the chat once you got it. I'm going to give you like 3 minutes to try and puzzle it out. All right, last call for the answer. We'll go over the result in 1 minute. All right. So let's split these into pieces. And we'll look at the conjugates. So the conjugate of NH4 plus is NH3. And the conjugate of Br minus is HBr. Ammonia is a weak base, which means that NH4 plus should be a weak acid. HBr is a strong acid, so its conjugate will be neutral. Since we're going to ignore things that are neutral, we'll take this one. And we'll make H3O plus and NH3. And since we made this, the solution would be acidic. All right. We'll put that on the screen there. There we go. All right, good job. So I'm going to give you 4 of these. And what I want you to do is I want you to tell me, will the solution that you put it in be acidic, basic, neutral, or unknown? My hint here is that you should have one of those 4 answers for each of those questions. So you're not going to double up on any of them. I'll give you 5 minutes to work it out. We're going to do 1, 2, 3, 4. We'll go over the answer, and then we'll do the last section of the class. We'll probably end up finishing a little early. One more minute, we'll go over the answers. All right, let's go over here. And get to work. So the first one, those are the ions it dissociates into. Let's look at the conjugates. All right, so this is strong, which means that this is neutral, so we'll ignore it. This is a weak base, which means that this is a weak acid. So the reaction that we would observe would be we have our weak acid and water makes H3O plus and ammonia. There you go. So the first one is acidic in solution. How about the second one? So we've got K plus, Br minus. All our salts are neutral. We can ignore them. Or our metal ions, I should say. HBr is a strong acid, which means that this is neutral. We'll ignore it too. And so we just end up with a neutral solution. All right, let's do number 3. Now we've got ammonium and hypochlorate. You don't know the names of hypochlorite and such. That's fine. Those are not on your polyatomic ions list. But we can do their conjugates. So the conjugate of NH4 is NH4 plus is NH3. And the conjugate of this is HClO. NH3 is a weak base, so NH4 is a weak acid. HClO is not a strong acid, so it must be a weak acid, which means that this is a weak base. And since I have one of both, then we don't know what the outcome is. A weak acid would make H3O plus, but a weak base would make OH minus, and those two would then neutralize each other. So we don't know which one makes more. We would need further information. And finally, the fourth one here, we got sodium, which is neutral, so we don't care about it. And then we got acetate, whose conjugate is acetic acid, which was not a strong acid, so that makes it a weak acid. Therefore, this is a weak base. And when we react that with water, if it's a weak base, it will make hydroxide and acetic acid. All right, so that's how you determine the pH of a solution once you've put a salt in it and the salt dissolves. All right, any questions, let me know. Well, here's the homework practice, so make sure we get that. There we go. And let's talk about buffers. All right, buffers are the last thing we're going to talk about in this class. We got 30 minutes. That's more than enough time. Buffers are important to your body for a very specific reason, and that reason is because you are exposed to all sorts of chemicals that are well beyond the normal scope of physiological pH. So physiological pH is 7.3. Stomach acid in your body is pH about 1.5 to 2. Soda that you consume is pH 2.5 or so. Some of it's lower than that, like Pepsi's around 2. Diet Crystal Pepsi, and I don't know where I found this picture. Like, these are like the oldest sodas I've ever seen. I don't know how many of these are still in production. I don't even know what Nehi is. I know what Mellow Yellow is, but yeah. So, anyway. The point is, you are exposed to ridiculous pHs as far as your body is concerned. Since your body needs to stay very, very close to 7.3, 7.4 pH, adding something with pH 1 to your bloodstream would be incredibly deadly. In fact, I want to calculate out that if it weren't for buffers, the amount of soda that you would have to drink to die would be on the order of milliliters. So like 5 milliliters of soda, less than a shot of Pepsi, would be fatal if you did not have a way to neutralize the pH. Because it would shove your pH of your body so far out of this tight range, around 7.4, you would just instantly die. And that makes sense, right? Because for pH 7.4... the amount of H3O plus in the solution, and we can go over here and do this. So 7.4 negative, and then 10 to the, so is about 4 times 10 to the minus 8 moles per liter. What about pH 1.5? So let's type that in and see what happens if you, how much acid is in pH 1.5. So 1.5 negative 10 to the, and we get 3 times 10 to the minus 2. So that's 100, that's a million times more acidic than blood. So your stomach is a million times more acidic than blood. Just a little bit of that stomach acid in your bloodstream, death. Game over, return to Ganon, right? Like, it would be terrible. So, fortunately, there is a physiological mechanism in play here that prevents this from happening. And it's called a buffer. A buffer is any combination of substances that resist sharp changes in pH. And the way that it does that is by having very specific components mixed together in similar ratios. And so we're going to click on this video here. Oh no, my browser is up to date, you guys. Not again. Okay, the second time I clicked on it, it worked. Okay. So let me get the window capture up here. Yep, that's the one I want. Boop. All right. On the screen here, you can see, I'm going to cover up everything to make this as big as possible. Oh, oops, hold on. Let's put the calculator behind so it's not in front. All right. On the screen here, you can see a solution of something in water. On the left is the unbuffered solution. Oops, I'm clicking on the wrong thing. There we go. The unbuffered solution. There's no buffer in here. And its current pH, according to this strip, is about 8. On the right, we have a buffered solution, and its pH is also 8. And what we're going to do is we're going to add strong acid and strong base to both of them, and we're going to see what happens to the pH. The pH will change colors. So if it's acidic, it will turn back to yellow, then orange, and all the way to red, depending on how much how quickly the pH changes. And then the other direction goes green and then towards blue and purple. So here we go. We're going to add 1 molar HCl. Remember, the pH of this is 0. We're going to add it to unbuffered distilled water. We're going to add 1 drop. Drip. That's it. What's the new pH? Holy shit, right? So we changed the pH of our water from 8 to now like 1 by just adding 1 drop of acid to it. That's ridiculous, right? And that's because there are a million times more, this is a million times more acidic than the solution we're adding it to. So even though it's diluted, its pH changes like crazy. Now, but when we add it to the buffered solution, nothing happens, you'll notice. In fact, we can add a whole bunch of it to the buffered solution. So we're going to add dropwise here. So 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going out of focus, isn't it? Yeah. 11, 12, 13, 14. I'm trying to count these for you. So you'll notice that after like 20 drops, now it's barely in the yellow region. Well, let's keep going. Let's see if we can actually change it here. $30, $33, $36, $40. I'm just estimating at this point. It's no longer green, so it's definitely acidic now, but it sure took a lot more just to get off of 8 and over to, like, say, pH 6 or something. And if we keep going, it will slowly turn towards orange and red. But certainly not as quickly as it did with the unbuffered solution. All right, we could fast forward through this part. Oops, hold on, I messed up. There we go. So the next thing we're going to do is we're going to add base. This is sodium hydroxide. This is 1 million times less acidic than water. We're going to do the same thing. We're going to add 1 drop, boop, to this. What happens to the pH? Whoop! We went all the way down to like pH 10. Oh, maybe we didn't. So that would have neutralized the acid that was added earlier. We're going to add 1 more drop, and now it should just be blue. Yeah, there you go. Now, if we do this to the buffered solution, it will slowly neutralize the acid that's in there, but it's going to take a lot longer, as you can see. So 1, 2, 3, 4, 5 drops. That's barely going to do anything. Seven, 8, 9, 10, 11, 12, 17. And we'll just fast forward here. And you can see how much, because he's entering the pipette the entire time. So he's doing it dropwise, but it takes a very long time to change the pH because we've added a buffer to it. And that's incredibly helpful for biology because we don't want to change our pH. We want our pH to remain constant, or at least close to it. How do you make a buffer? A buffer requires 2 components. You need to have some weak acid, and then you also need the conjugate weak base of the weak acid. So, for instance, if I had a weak acid, we'll say HClO2. I would also need to add the conjugate base of that weak acid, which is also a weak base. And then I would add that as some sort of salt. And so I would do this to it. So these 2 things together would make a buffer. Because I have a weak acid, that's this one, and then I have a conjugate weak base, which is this one. They have to be conjugates. If you have any weak acid and weak base, you don't get a buffer. They must be conjugates. which is why we did the whole previous section on what's the conjugate of this. All right. This is the phosphate buffer at the bottom here. The phosphate buffer regulates the pH within cells to be very close to about 7. And so we have a weak acid there, H2PO4-, and its conjugate weak base is H2PO4- with an H plus removed. So we get HPO4 with a 2- charge. So I've taken away this H, and I've made this 2- to get to that. Now remember, the whole thing about conjugates is the difference between them is always H+. So if you don't know what the conjugate of something is, try removing an H+ from it, or adding an H+ to it. All right. Which of these is a buffer, and which ones are not buffers? Oops. There we go. So I want you to tell me over here. So I'm going to go 1, 2, 3, 4. I want you to tell me which ones are buffers. I'll give you a hint. Only 2 of these are buffers. For the ones that are not buffers, why are they not buffers? Which part of the rules were broken to create that mixture? So I'll give you 2 minutes to puzzle this out. Then we'll go over the answers together. All right, 1 more minute. We'll go over the answer. All right. So for this first one here, these differ by only this H+, right? So these are conjugates, so this would be a buffer. And they're both weak. This is a weak acid. This is a weak base. For number 2, this is a strong acid, right? So strong acids cannot make buffers. So this is not a buffer. Down here, these are both weak, but they're not conjugates. So it's not a buffer. This one is a buffer, and we'll show why here. So if I split this into pieces, remember, we don't care about these sodiums. I get this one, and then I also get 2 more sodiums, which we don't care about, and carbonate. These are conjugates of each other, and they're both weak. So therefore, we would make a buffer. This would be a carbonate buffer. The carbonate buffer is what's in your bloodstream. When you breathe in oxygen, your body combusts the oxygen in, I want to say it's the mitochondria where this happens. And you create CO2 from there. Then the CO2 goes into your bloodstream and reacts with water to form bicarbonate, which is part of a buffer. Well, it forms carbonic acid, which can then become carbonate and then bicarbonate. Or other way around. Anyway. All right. How do buffers resist changes in pH? Well, I have a weak acid and a weak base in the solution, right? So let's look at the phosphate buffer here. The phosphate buffer, here's my weak acid. And the weak base, which would be this part. These are both present in the buffer. Let's suppose that I added hydroxide. This is a strong base. We need to neutralize it or else the pH will go up real quick. How do we do that? Well, if a strong base reacts with a weak acid, this gets neutralized and I form this, which already existed in the solution, right? So I will turn this into water, and all I'm doing is creating the other component of the buffer in doing so. If I create the other component in the buffer, the pH won't change very much because it was already there, right? I am getting rid of the strong thing and turning it into a weak thing, in other words. So we'll show that here. Likewise, we could do the opposite with adding acid. I have my weak base in the solution. So here's my weak base for my buffer. I also have the weak acid component of the buffer. My H plus adds to this to neutralize it. And I make the weak acid part of the buffer, which also is already there. So the pH doesn't change very much. I've turned something strong into something weak. And then the Cl minus we just ignore because it's neutral. So that's how buffers work. You have a weak acid, you have a weak base. Whatever you add to it as a strong acid or a strong base, the component that would react with that consumes it. And as a result, the pH doesn't change very much because the products are things that are already there. All right. So there you go. That's buffers. We can use acid to neutralize, or we can neutralize our acid with the weak base part of the buffer. We can neutralize base with our weak acid part of the buffer. All right. Now, it is possible that you can add so much acid or base that the buffer won't function anymore. You can overwhelm a buffer. So it is important to note that buffers are not completely immune to the effects of pH resistance. If you add too much, it will fall apart. For example, if I have X amount of the weak acid and then X amount of the weak base, and I use up all of this, then any further base added would not be reacted with, and that would be an issue. So buffers are not immune to pH changes, but they resist them greatly until the buffer is depleted. All right. There's unfortunately no time to do these problems because we've reached the end of the lecture, so I do just want to put the homework question up here. If you have questions about these on-screen problems, I'm happy to answer them in the Discord. Just paste questions in there. You know, when Discord's actually working, it wasn't working today. But that's it. That's everything. Congratulations. There's no more content. There's nothing more I have to teach you. You've seen everything there is to know about chemistry. That's not true, necessarily. But you've seen everything there is in this class. And hopefully you got something out of it. So I just want to thank everybody for not just coming to the lecture today, but for being a part of Chem 121. We're going to have one last session tomorrow, which is a review session where you may ask me anything that you would like. So make sure you show up for that. Get quiz number 8 in tonight before it closes. Get quiz number 9 in before it closes on Wednesday. And make sure you're studying for that final. Or midterm number 2, actually. All right, I'll see you for the review tomorrow. Bring questions, and good luck on the exam.